I'm Jaden, and I'm going to talk about how remote sensing can monitor climate change, and more specifically, how the GRACE mission has been used to look at ice sheets and ice sheet instability and its contribution to sea level rise. So, sea level rise is one of the major consequences of climate change. It's caused by multiple different processes, like the thermal expansion of oceans, melting of glaciers and ice caps, changes in the water storage on land, and the melting of ice sheets, all of which can be tracked back to climate change or global warming and the heating or increasing temperatures that we're experiencing. So these different contributions, it's important to understand the size and uncertainty of each of them in order to understanding how they're going to affect sea level rise. So, in order to understand how it affects sea level rise, it's important to look at different monitoring strategies of sea level rise. So, in recent years, sea level change and understanding the causes of it has improved a lot from in situ and remote sensing techniques. Since the early 1990s, satellite altimetry has been the main tool for precisely and continuously measuring sea level. So the concept of satellite altimetry is shown here in the diagram on the right. So up here you have the radar altimeter, which transmits microwave radiation down to the surface of the sea. This is partly reflected back up to the satellite, which measures the round trip travel time. And from this, you can determine the height of the satellite above the sea surface, which gives you the range. So, if you take a variety of recordings in this same location, you're able to detect changes in things like elevation or sea surface height. It's really important when making measurements from remote sensing techniques and satellite altimetry to correct for different factors like atmospheric delay in order to get an accurate measurement of what you're trying to measure and not have different things conflicting with what you want to be measuring. So for the focus of this, we're going to look at how ice sheets contribute to this sea level rise. The IPCC did a workshop about sea level rise and ice sheet instability, and in their report they say that the largest uncertainty regarding sea level rise is actually associated with the response of how large ice sheets will respond to climate change and what their sensitivity is to climate change. So, because of this, it's really important to understand the dynamics of ice sheets and how they are changing and how they've changed in the past. This has improved a lot since the 1990s, similar to monitoring of sea level rise. Since then, they've also begun using different remote sensing techniques to look at mass changes in ice sheets. So, for example, using radar altimetry, satellite altimetry, which monitors ice sheet elevation change. The two major ice sheets are Greenland and the Antarctic ice sheet. The contribution from these large ice sheets has an incredible potential of affecting sea level rise. So, for example, in the article by Casanave, they discuss what would happen if Greenland and Antarctica would completely melt, and they say that sea level would rise by 7 and 3 to 5 meters, respectively, which would cause enormous changes around the globe. Observations over the past 2 decades have shown rapid acceleration in the melting of the ice sheets. So, because of this, the potential impact that further sea level rising could have, and the fact that the ice sheets are accelerating in their melting, shows that it's really important in order for us to monitor what's happening with them in order to plan for the future. One of the most important satellites related to remote sensing techniques in assessing changes in ice sheets and sea level rise is the GRACE mission, or Gravity Recover and Climate Experiment. Um, so this was launched in 2002 and had the goal of accurately mapping variations in Earth's gravity field. They have two identical spacecrafts which fly about 220 kilometers apart in a polar orbit 500 kilometers above the Earth. The image here shows the two aircrafts. It is definitely not to scale. In reality, the two satellites would be a lot further apart, but just sort of gives you an idea of what they look like. So how do the GRACE satellites work? There are two spacecrafts, GRACE 1 and GRACE 2. So in these images, the satellite on the left would be GRACE 1 because it's the first one in the flight direction and the other one's following it. So two satellites, one flies behind the other as they circle the Earth. There is a K-band ranging instrument on each of them, which calculates the precise speed of each satellite and the distance between them, and is constantly communicated using a microwave K-band ranging instrument. As the satellites move over the Earth, the gravitational field changes beneath the satellites in correlation to changes in mass or the topography of the surface beneath it. As this happens, the orbital motion of each satellite is changed, which then causes the distance between the two satellites to change, and this is measured using the K-band instrument. So this change in motion, which is measured by the K-band instrument, allows us to determine changes in the Earth's gravitational field. The most important parts of the satellite can be seen on here. To demonstrate how this helps us understand ice sheets and sea level rise, we're going to look at two different examples or two different papers that have been done. So the paper done by Remelian in 2006 looks at determining spatiotemporal changes of ice sheet mass balance. In the paper, they discuss how remote sensing has allowed us to make direct observations on the mass balance of Greenland and Antarctica. Satellite and airborne altimetry measure ice elevation, which means that you need to correct for snow compaction, but GRACE directly measures the total change of the mass change of the ice sheets, which makes it more useful. So in their study, they analyze GRACE data to determine spatiotemporal change of the mass balance in Greenland and Antarctica ice sheet over a 3-year span from 2002 to 2005. Unfortunately, one of the downfalls of GRACE is that it's sensitive to solid Earth movement, particularly glacial isostatic adjustment, or GIA, which refers to the adjustment of crust and mantle in response to the last glaciation. So in their study, they corrected for different things like leakage and the GIA, and they estimate that ice sheet contribution to sea level. They find that in West Antarctica and Greenland, there's a positive contribution to sea level, but in East Antarctica, there's actually an increase in ice sheet mass. They found their results are in general agreement with other observations that suggest East Antarctica ice sheets are slightly gaining mass while West Antarctica is losing. The image on this slide gives a good idea of how the data that they found can be used to monitor changes in ice sheet mass and the amount of change that is occurring. At the end of the study, they found that the total ice sheet contribution to sea level is about 0.5 millimeters per year between the range of 2002 and 2005. But it's important to note that this was a really short study, so the results have to be considered quite preliminary. So the next study was done by Velikogna in 2009. Here they looked at monthly measurements from GRACE in order to determine mass loss of the Greenland and Antarctic ice sheets from 2002 to 2009, which is longer period of time than the previous study. And they conducted this study because observations had been made that ice sheet loss was actually accelerating and not occurring in a linear fashion. So they used this study and GRACE data in order to see if this was true. In their solution, they applied many different corrections. For example, they used a different spherical harmonic coefficient because the one that GRACE uses has a lot of variability. So they replaced it with values taken from satellite laser ranging. They also use an averaging function that minimizes the combined measurement error and signal leakage. So they were finally able to obtain a time series for the ice mass changes calculated from GRACE monthly mass solutions from April 2002 to February 2009. The two graphs shown show the decrease in ice mass, and the lines don't really appear straight, they appear curved, which fits the idea that it's not occurring in a linear way, it's actually accelerating. So because of their observations, as you can see on the graph, they chose to use a quadratic fit instead of a linear. Because of the acceleration, the quadratic fit of their data worked a lot better. After their detailed analysis, they say that it unambiguously reveals an increase in mass loss from both ice sheets. They also find that the combined contribution is accelerating at a rate of about 56 gross tons a year, plus or minus 17 gross tons per year squared. This leads to an acceleration in sea level rise of 0.17 plus or minus 0.05 millimeters per year squared. Both of these studies show how ice sheets can contribute to sea level rise and how ice sheet instability is changing, how sea level rise is changing, which sort of implies why it's important to plan for the future because of the changes that are very likely to occur. So just lastly, why does it matter? Why should we be continuing to look at sea level rise and the ice sheet contribution? There's a lot of different impacts that future sea level rise is going to have. For example, physical impacts include things like flooding, wetland loss, shoreline erosion, saltwater intrusion in freshwater bodies and aquifers on land, rising of the water tables, etc. So not only are these physical impacts, but these are also impacts that are going to affect society and the economy. Depending on the severity of sea level rise or the amount, the impacts will likely be felt worldwide, but to different degrees. The most severe impacts will definitely be felt by areas in vulnerable low-lying coastal regions. But because of the complexity of sea level rise and the multiple contributions that can lead to sea level rise, it has the potential to affect the population worldwide, which means that it's very important to continue monitoring it and better understand how it is occurring.